Welcome back to Engineering Acoustics. Hi, this is Professor Ryan Harne. In this video, we'll learn about harmonic acoustic waves. We'll also gain new intuition regarding the relationships between time and space in acoustics.
So let's get started. Let's recall the one-dimensional acoustic wave equation, which is the second partial derivative of pressure with respect to x is equal to 1 divided by c squared, where c is the phase speed or sound speed, multiplied by the second partial derivative of acoustic pressure with respect to time. D'Alembert found in 1747 that the general solution to the acoustic wave equation was a combination of functions, f1 and f2, that have arguments ct minus x, which meant waves propagate in positive x direction, and the other argument for f2 is ct plus x, which meant that waves propagate in the negative x direction. Let's see if we can find functions f1 and f2 that satisfy the acoustic wave equation. Let's try out sine. So our first function has an amplitude that we don't know yet, a 1, with the function sine as a function with argument k times the quantity ct minus x. So we include k since maybe there's a constant there that we're not aware of. This is the use of this constant term. The argument ct minus x is then present, and we have our second function which has amplitude a2 multiplied by sine with the argument k ct plus x. This type of one-dimensional realization is similar to a long infinite duct in both directions, where it extends infinitely out into positive infinity if our x origin is somewhere in the center of the infinite duct, and the duct also extends into negative infinity of values of x. So what we need then is to substitute this P, assumed acoustic pressure, back into our wave equation. So after simplification, we find that these partial derivatives, del squared p, del x squared, this partial derivative is minus k squared p, whereas the second partial derivative on time of acoustic pressure is minus k squared, c squared, and p. So when we substitute these derivatives back into the acoustic wave equation, we have minus k squared p is equal to 1 on c squared of minus k squared c squared p. And this, in fact, is an equality. It works. So this satisfies the acoustic wave equation. What's interesting is that we can repeat this exercise. And what we'll find is that all functions that have arguments ct minus x and ct plus x satisfy the acoustic wave equation. And this means that waveforms like sine, cosine, even the complex exponential, indicating or recognizing that only the real part is the physical part, all of these functions satisfy the acoustic wave equation. But specifically sine, cosine, and this complex exponential, these are harmonic functions. Specifically, they're periodic. And they're periodic in both x space and time t. We refer to these periodic waves as harmonic waves. So let's consider these harmonic waves further. Let's consider a semi-infinite duct. It extends forever in the positive x direction, but terminates in a rigid piston at x is 0. This piston displaces with amplitude capital D and a harmonic or periodic frequency omega in radians per second. This piston will create acoustic waves in the duct. And since there are only positive x traveling waves, we only have the functional argument ct minus x in this case. So let's learn about the harmonic waves created through this piston oscillation. The boundary condition in this problem is that the velocity of the piston, let's write that as lowercase d dot, must be equal to the fluid particle velocity, u, at location x is 0, and it must be equal for all time. So d dot is equal to minus omega capital D sine omega t. This is equal to our particle velocity, and u is x of 0 and time t. So to find the particle velocity relationship, we need to recall Euler's equation. Euler's equation was the relationship between acoustic pressure and particle velocity through a relationship similar to Newton's second law. That relationship in one dimension was del P del X is equal to the atmospheric density rho naught multiplied by del U del T. And here, by using our assumed solution form for acoustic pressure, we find that the particle velocity U as a function of x and t is 1 on rho naught c multiplied by an amplitude A of sine, that's a function of the unknown constant k, multiplied by ct minus x. Let's apply the boundary condition to determine these unknowns, amplitude A and constant k. So the boundary condition is that the fluid particle velocity at x is 0 must be equal to the piston velocity due to continuity of the motions of those surfaces and particles. So the piston velocity is minus omega d sine omega t. This must be equal to the fluid particle velocity, which is 1 on rho naught c multiplied by capital A, the amplitude, and then the sine function with argument k multiplied by ct minus, and it's no longer x since we're applying the boundary condition, so it's minus 0 here. Now, in order for this to be true, two things need to be true. Firstly, the amplitudes need to be equal, which is an equality of minus omega capital D is equal to 1 divided by rho naught c multiplied by A. The second thing that has to be equal are the sine arguments. And we've got sine omega t on the left-hand side of that equation and sine of k multiplied by ct on the right-hand side. So this is omega t must be equal to k c t. So working these out, we find that the amplitude A is now known, and it is minus omega rho naught c multiplied by capital D, the piston displacement amplitude. This is the amplitude of the acoustic pressure. The unknown k is found to be omega on c. The units of this are 1 on meters, are also occasionally but less often written as radians per meter. This constant k is called the wave number. It's an important characteristic of acoustic waves that we'll revisit throughout this course. So summarizing what we found, the acoustic pressure P as a function of x and t is minus omega rho naught c capital D sine as a function of omega on c multiplied by ct minus x. So we can simplify this last part and make it minus omega rho naught c d sine of quantity omega t minus kx. What we've just determined is the solution for acoustic waves traveling in a one-dimensional long pipe or duct. These are called plane waves, and every cross-sectional slice or plane along the axis of propagation, the acoustic variables are constant. We can simplify the solution for plane waves using complex exponentials. If we start this problem over and now use the complex exponential function e to the j of k times ct minus x, we find the same results. The wave number is still omega on c, and the amplitude is now complex, which has value j multiplied by omega rho naught c and capital D. If we substitute all these things back in, solve for the real part, after lengthy simplifications, what we find is that the acoustic pressure P as a function of x and t is minus omega rho naught c multiplied by sine omega t minus kx. In other words, the real part of the complex exponential solution is the actual response. It is the measurable response, and it is in fact the solution we had on the prior slide. One thing to note that we'll use in this course is that in the complex exponential form, the acoustic particle velocity, which we now recognize should be underlined, is written in the following way. It is plus and minus of the complex acoustic pressure of x of t divided by rho naught c, where the plus and minus indicate the vector directions of acoustic particle velocity. Let's look more at the periodicity of these waves in time and space. So we just determined the acoustic pressure of harmonic plane waves in a duct. It has an amplitude, capital A, multiplied by sine with argument omega t minus kx. Let's look at periodicity in time first. So for a fixed point in the duct, which could be any point in the duct, the phase repeats in time every 2 pi radians. So we have that P is equal to A sine omega t plus 2 pi minus 0, and we'll use x is 0 in this example. We can introduce a new term to simplify this. P is equal to A sine omega t plus omega capital T, where capital T is the period. It has units of seconds, and it is related to the angular frequency omega by T is 2 pi on omega. In plots, we often see the frequency shown in hertz. We'll denote that here as lowercase f, which is frequency, and it has units hertz, in other words, 1 on seconds. Frequency is the inverse of period, so that we can express here t, the period, is equal to 1 on f. This shows that omega is equal to 2 pi times f, showing the relationship between angular frequency omega and frequency. What about the periodicity of waves in space? For a fixed time in the duct, again, it could be any time, the phase repeats every 2 pi radians. Let's perform the same exercise. The acoustic pressure P is equal to an amplitude A multiplied by sine, I'll use time 0, minus kx minus 2 pi. Introducing a new variable to simplify this, we have the acoustic pressure P is equal to A sine minus kx minus k lambda. Lambda, we've seen before. It's called the wavelength and has units of meters. The wavelength is computed from 2 pi on k. Recalling that k, the wave number, has units 1 on meters. We know intuitively that waves develop in both space and time and acoustics, but what are the relationships between the period, the frequency, the wavelength, and the wave number? We've previously seen this schematic where fluid particles in this fictitious chain begin propagating waves in both time and space. Let's then write out these variables that we've just defined. We have the period, t, and this has units seconds. We have the frequency, denoted by omega, which has units radians per second. We have the wavelength, which we use the Greek lambda term to denote that, having units meters. And we have wave number, which is the k variable we used before, which has units 1 on meters. It's also occasionally seen as radians per meter. So how do these parameters show up in a plot of the waves developing in both time and space? Well, we can see this wave developing here in time, and we see that It has approximately 2 peaks, maybe a little bit more over the duration that's shown. The distance between this common point of phase of the peak is the period. Now if we look in space and we look from one peak to the next, the distance from space from one point of peak to the next, we track this distance. This is the wavelength. So what's the relationship between period and wavelength? This is communicated through the sound speed. By rearranging our equation for the wave number, k is omega on c, we find that c is omega on k. So the sound speed is that proportionality between space and time in acoustics. So let's summarize what we've learned. Harmonic waves in one dimension are often mathematically represented by complex exponentials. It simplifies the mathematics considerably, but we have to recognize that only the real part is physical. Space and time have related wave metrics. So here's an analogy for you. Frequency is to period as wave number is to wavelength. They are related through similar trends. Space and time are related to the sound speed specifically, and this is a function of the fluid properties.
That's it for this video. Now that we've learned about one-dimensional plane waves, in the next video we'll learn about the waves that we're most commonly exposed to day to day. Those are spherical waves.